Hello, and welcome to the TI Precision Lab covering component selection for SAR ADCs. The goal of this section is to select the proper bandwidth amplifier and external RC filter components for the input drive circuitry. This section will also show how performance can be verified and optimized using Tina Spice. This video starts with a simplified explanation of a SAR converter operation. Next, it provides guidance in using Texas Instruments Parametric Search tool to find the right data converter for your application. Finally, the video covers how you can use a software calculator to find initial amplifier and RC filter values. These values will be used in subsequent videos for Tina Spice optimization of the circuit. This slide shows the overall process that we will walk through to select the external components for the SAR ADC. These steps will be covered in several videos. This video will walk through the first three steps. Let's start by going through an overview of how a SAR ADC operates. A SAR data converter conversion cycle can be broken into two different phases, the acquisition phase and the conversion phase. During the acquisition phase, the goal is to charge the converter's internal sample and hold capacitor to be equal to the amplifier's output voltage. In practice, it is sufficient for the converter's internal sample and hold capacitor to settle to an accuracy of less than 1/2 of an LSB, as settling to a higher degree of accuracy will not improve ADC accuracy due to quantization noise. Notice that switch S1 is closed at the beginning of the acquisition phase and is opened at the end of the acquisition phase. Depending on the conversion rate, the acquisition time may be very short. For example, a 1 megasample per second converter acquisition phase might be 300 nanoseconds. Because this acquisition may be very short, it is often necessary to use wide bandwidth amplifiers to achieve the desired accuracy. Also, selecting the correct external RC charge bucket circuit has a significant impact on settling. The goal of this presentation is to develop a method for selecting the appropriate bandwidth amplifier and the best values for the RC charge bucket filter. This slide covers the details of the conversion phase. At the start of the conversion phase, the switch S1 is open and the amplifier's output is stored on the sample and hold capacitor from the acquisition phase. In this case, you can see that the sample and hold capacitor has 2.6 volts stored on it, which is the amplifier's output. The conversion phase process will do a comparison for each bit. This is a 5-bit converter, so 5 comparisons will be done starting with the most significant bit, or MSB, and moving to the least significant bit, or LSB. Here we see the result of the first comparison for the MSB. The in-bit DAC applies a signal to the negative input of the comparator equal to 1/2 of the full scale, or 2.048 volts in this example. The other side of the comparator is connected to the 2.6 volts from the sample and hold capacitor. Since the sampled voltage is greater than the DAC voltage, the output of the comparator is logic 1. The MSB voltage will remain on, and subsequent DAC outputs will include this value. For the next comparison, the DAC applies an additional 1/4 full scale so that the DAC output is 3.072 volts. This is greater than Vn, so the output of the comparator is a logic 0. Notice that the in-bit register accumulates the results. Since the DAC test voltage is greater than the input signal, this bit is turned off and will not be included in subsequent tests. For the next comparison, the DAC applies an additional 1/8 full scale so that the DAC output is 2.56 volts. This voltage is less than Vn, so the output of the comparator is a logic 1. Since the DAC test voltage is less than the input signal, this bit is turned on and is included in the subsequent tests. Notice that the register now has the results from the first 3 tests. The process repeats and you can see that this comparison exceeds the input signal, so the bit is 0. The least significant bit is done last, and you can see that this bit is also 0. After this test, the final conversion result is stored in the in-bit register. This process is basically a binary search where the object is to get the DAC output to match the stored input signal. The final step in our conversion model is to reset the sample and hold capacitor by closing S2. Strictly speaking, this reset might not happen in the actual converter. However, in practice, the capacitor charge is altered during the conversion process. The actual final charge on the capacitor will differ from device to device and may not be specified in the ADC datasheet. Assuming the internal capacitor is reset to ground at the end of the conversion is a conservative worst-case approach. Following this model will yield robust results and leave margin for process variation. The potential downside of designs based on this assumption is that they may require amplifiers with wider bandwidth than is needed. The overall objective of this video is to provide a design method that will facilitate the selection of the amplifier and external RC charge bucket circuit. For the RC charge bucket circuit, we will find values of R and C that facilitate settling, but also maintain stability for the amplifier. The capacitor in this circuit provides a large reservoir of charge that will provide a quick charge dump to the internal sample and hold capacitor at the start of the acquisition period. This resistor helps maintain stability on the amplifier as it cannot directly drive the charge bucket capacitor. The charge bucket capacitor will get the sample and hold voltage close to the final target shortly after the switch is closed. The amplifier needs sufficient bandwidth to complete the settling to less than 1/2 LSB by the end of T acquisition. It is possible to directly drive a SAR converter without the RC charge bucket circuit, so why don't we just omit this circuit? This example shows the same data converter being driven by two different amplifier configurations. Both configurations have good settling, but the top circuit doesn't use a charge bucket circuit. Notice that the required bandwidth for the top circuit is 130 MHz, and the bottom circuit only has a bandwidth of 20 MHz. This makes sense as the purpose of the charge bucket circuit is to facilitate quick settling by dumping charge into the internal sample and hold circuit at the beginning of the acquisition period. Without this initial boost, a much faster amplifier is required. In general, it is recommended to use lower bandwidth amplifiers if possible, assuming the settling is adequate. The reason is that the lower bandwidth amplifiers tend to have lower quiescent current, better offset, and lower input bias currents. Furthermore, these devices may be lower cost and are often less sensitive to stability issues. For wide bandwidth amplifiers, it is often necessary to be careful of any parasitic capacitances from a stability perspective. Finally, another benefit to the RC circuit is that it band limits the noise. As mentioned previously, the RC charge bucket does not act as an anti-aliasing filter, but it does help with noise. Let's move on to the second step where we select the data converter. For this example, our design goal is given in the lower right-hand corner. 16 bits, sample rate of 100 kilosamples per second to 1 megasample per second, single-ended input, 5-volt input range, and SPI interface. There are over 500 different precision data converters to choose from. Here, we will briefly cover how to use TI's parametric search to find the converter that meets your requirements. From the main TI.com web landing page, click on Data Converters under Browse Products. Next, under Data Converters, select Precision ADCs. In this example, we need a resolution of 16 bits, and a sampling rate between 100 kHz and 1 MHz. After selecting these options, we have reduced the number of options from 535 to 71. Next, select a single input channel and a 5-volt maximum input range. Finally, select a SPI digital interface and a single-ended input. This reduces our choices to 4. From that group of 4, we will choose the device with the highest sampling rate, the ADS-8860. The main point here is that the parametric search filters can be a quick way to find the device you need. Let's move to the third step, where we walk through how to use a software tool to find the amplifier and RC charge bucket filter components. For this, we will use the ADC SAR drive calculator to find the starting values used in Tina Spice for optimization. This slide summarizes and defines the information needed for the software calculator. The full-scale range is the range of voltage that is applied to the converter for valid conversions. Typically, this is Vref or a multiple of Vref. Resolution is the number of bits used to represent the digital equivalent of the analog signal. In this example, we use a 16-bit converter that has 2 to the 16th or 65,536 codes. CSH is the sample and hold capacitance, sometimes called CN. Typically, this is between 10 picofarads and 100 picofarads. RSH is the on resistance for the sample and hold switch. This is typically between 10 ohms and 100 ohms. Normally, this information is in the datasheet equivalent circuit. TAC is the acquisition time. This is the duration that the sample and hold switch is closed. A longer acquisition time makes it easier to settle. The datasheet provides a minimum acquisition time that corresponds to the maximum throughput in samples per second. This slide shows where you would find the information required for the software calculator in the datasheet. The full-scale range and resolution are normally listed in the specifications table. Notice in this example that the full-scale range is Vref and the resolution is 16 bits. The internal sample and hold capacitor, CSH, is sometimes called input capacitance. This is listed in the datasheet table or shown in the equivalent input circuit. Notice that this example datasheet shows an input capacitance specification of 59 picofarads and an equivalent input circuit sample and hold capacitance of 55 picofarads. The reason for the discrepancy is that the equivalent circuit separates the 55 picofarad sample and hold capacitor and the 4 picofarad parasitic input capacitance. So CI from the table is the sum of the 55 picofarads and 4 picofarad capacitors. Note that when we build our input model, it is best to refer to the input circuit for completeness. The sample and hold resistor, RSH, is usually found in the equivalent input circuit. Some datasheets don't have any information on the sample and hold resistor, RSH. One way to estimate this resistor in cases where it isn't specified is to use the equation here. Divide the minimum acquisition time by 100 times the sample and hold capacitance. Using the datasheet information for this example, we estimate the resistance to be 53 ohms, and the actual resistance is 96 ohms. So the estimate will not always be perfect, but it will give a reasonable approximate value. Throughput is the total time required to acquire and convert the signal. The throughput can be determined by adding the maximum conversion time and the minimum acquisition time. The acquisition time is another specification required for the software calculator. If the converter is running at maximum throughput, you can use the minimum acquisition time in the calculator. In cases where the converter isn't running at maximum throughput, the acquisition time can normally be calculated by subtracting the maximum conversion time from the throughput time. This is because the conversion timing for this example is set by an internal clock. Once the conversion is complete, acquisition will start. Therefore, to find the acquisition time, you subtract the maximum conversion time from the total throughput time. Note that this is true for most devices, but for some devices, the conversion may be controlled by other means, so be careful to read through the datasheet and pay close attention to the timing diagrams. Finally, it should be mentioned that increasing the acquisition time will reduce the bandwidth requirement of the amplifier driver. This is because we have a longer time period where the internal capacitor is charging, so a slower amplifier can be used. Also, increasing the acquisition time will reduce the total power. This is because little to no power is consumed during acquisition. Now that we have collected all the required information, let's use the calculator. The URL for this tool is located at the bottom of the slide. At the top of the calculator, first select the ADC input type. For this case, we are using a single-ended configuration with ground sense. Notice the schematic circuit at the right shows the selected configuration. Next, enter the resolution, input sample and hold capacitor, CSH, full-scale range, and acquisition time. Press OK and the value of the range for the filter resistor and capacitor is given, as well as the gain bandwidth for the amplifier and the maximum error target. This information will be used to set up our SPICE simulations. The next video will walk through steps 4 and 5 of the process. That concludes this video. Thank you for watching. Please try the quiz to check your understanding of this video's content.